It's hard to believe this is the normal behavior of water drops in weightlessness. It's even more remarkable that these free-floating drops can help us understand atomic nuclei, crystal growing, even the formation of stars. Scientists in many fields are vitally concerned with fluid behavior. I was the scientist pilot on the second manned mission of the Skylab space station. Our research included many experiments with fluids, demonstrations which can't be done on the ground. I'd like to share with you some of the discoveries we made and some of their implications. In the weightless environment of an orbiting spacecraft, surface forces dominate the behavior of water drops. This surface tension is caused by the inward pull of interior molecules on the ones near the liquid surface. Such cohesion prevents the escape of molecules from the liquid. The same surface tension acts on Earth too, but here, gravity and the need for support forces prevent drops from coming into equilibrium under the influence of surface forces alone. Small drops of water do form, but they last too short a time for us to manipulate them. On a hot surface, tiny, almost spherical drops are preserved by their own cushion of vapor. Under some conditions, surface tension effects are easily visible on the ground, as in making soap bubbles. In flight, we found it difficult to keep a water drop where we wanted it for close examination or for the camera. We were able to take advantage of surface forces by tethering blobs with a thread. Incidentally, all these drops are just water with ink or juice added for visibility. The adhesive or sticking aspect of surface tension was demonstrated nicely in Skylab. Here you see water pulled up by a drinking straw. In this unique demonstration, the crewman pinched the drop too rapidly for it to change shape smoothly. The resulting instability led to partial breakup of the drop. Handling of fluids was, of course, required every day to quench our thirst. The usual way was to use an accordion-like plastic bottle to squeeze the drink into our mouths. However, Bill Pogue wanted to see if adhesion would permit the use of an open-type drinking vessel.
A difficult operation to do in zero gravity. Every time you try to take a drink in zero gravity, of course, the water just goes every direction. And the water is contained in this container so strongly that I can actually squirt the water in there with this water gun, and it will stay in there. It's going in there with some degree of force. So in the process of actually doing this experiment, we discovered a fairly interesting fact. Now I'm going to take a drink, the first cup I know of that was actually been used in zero gravity. Works fine.
Freely suspended or lightly tethered, a water drop is spherical. In equilibrium, the attractive surface forces produce this most symmetrical of shapes. When a water drop is rotated, it is elongated by centrifugal forces that tend to pull the drop apart. Meanwhile, the cohesive surface forces act to hold the drop together. A drop rotating fast enough will break apart. Scientists are puzzled by the long delay before this one split. The question is complicated by the presence of an air bubble which may have weakened the neck of the drop. In any case, the higher the speed of rotation, the more the water drop takes on a so-called dog bone shape. This shape is also characteristic of some tektites, which are glassy rocks whose very presence on Earth is mysterious. The tektites evidently were once hot, molten, and tumbling in midair. Some of them cooled rapidly and froze into shapes like the elongated Skylab water drops. Others froze into even stranger shapes. In composition, tektites resemble neither volcanic material nor meteorites. They may have formed in the liquefying impact of a fiery meteorite with sand on Earth. They could have come from the moon or another planet. They might be material kicked onto a collision course with Earth by a huge meteor. Nature has also given the splitting drop a place in a submicroscopic world of atoms. In some ways, an atomic nucleus behaves just like a liquid drop. A heavy nucleus, like uranium, contains numerous protons and neutrons, nucleons, which attract each other like the countless molecules of a water drop. Therefore, a nuclear drop also has surface tension holding it together. But the protons are positively charged. They repel each other with forces almost as strong as attractive nuclear forces. The balance is so delicate that even small disturbances can trigger nuclear fission. From the tiny world of the atom to the stars and planets is an enormous jump. But our analog of fluid behavior also applies to the gas and dust drifting through the universe. The sun and planets may have condensed from a rotating, shrinking, fluid-like cloud 1 billion miles across. As such a cloud contracts under the influence of gravity, it forms a disk, and it heats up and then rotates faster and faster. What happens next is poorly understood, but many scientists feel that fragmentation of the cloud is most likely. If the cloud breaks into one large piece and many small ones, the result could be a solar system like ours. If there are several large fragments, each may condense into a star. Presumably binary stars were formed in just this way. Astronomers have observed countless examples with periods of revolution ranging from a few hours to hundreds of years. Galaxies may also have arisen from fluid-like clouds of gigantic mass. A rotating spiral of 100 billion stars is a typical stable state for such an enormous system. But stranger-shaped galaxies are also common. The dynamics of galaxy formation is one of the great unsolved puzzles of astrophysics. Although most of the applications of our demonstrations lie in the theoretical realm, some may soon be turned to practical use. Our most thorough investigation of fluid behavior on Skylab has indeed aroused new interest in several fields of technology. Here, for example, Ed Gibson set up a rig for rotating 2 socket wrenches with a zone of colored water between them.
And these mounts are pretty much the same as hold up the TV camera, line them up, taking some of our tools, which are extension shafts for some of the bits that we have and mounted them in here so that they're free to turn. We'll be placing a fluid in between the two here, which you'll be able to get a close-up view on this camera. And then we're going to turn it. We're going to turn both of them simultaneously using this string and rod, pulling it up. We can change the speed, we can rotate them in opposite directions, and we can also move the distance apart. We'll be placing colored...
A similar arrangement is important in growing large, high-purity rods of semiconductor material vital in the electronics industry. On Earth, a molten rotating zone of silicon or germanium is uniformly cooled between vertical rods. Convection currents due to gravity are still present, limiting the size and purity of the crystals. In orbit, there is negligible convection. Bigger crystals can be grown. In the 1980s, this technique may be used to grow semiconductor crystals of unprecedented quality. It is extremely difficult to predict exactly what will happen when two drops collide. But the collision and merging of drops is important in nature. In the fusion of atomic nuclei, two nuclear drops join to form a heavier nucleus. By studying events like these, physicists may learn how to make super heavy elements. The collision of tiny drops is also crucial to development of a rainstorm. In certain clouds, raindrops form by a complex process of condensation and merging of microscopic droplets. This process is not completely understood. Detailed studies of water drops in weightlessness could lead to a breakthrough in cloud physics. In the near future, many more experiments with liquids will be done in orbit. Applications are possible in meteorology, materials handling, nuclear physics, and astronomy. But already we have learned that a liquid drop in weightlessness can model the behavior of a tiny atomic nucleus or a giant galaxy. With models of such convenient size, we are thus given a new view, a glimpse into worlds of the very small and the very large.